Walk onto any modern factory floor, and you are immediately confronted by the overwhelming physical reality of production. Massive steel presses cycle violently, precision tools cut at high speeds, and complex conveyor networks operate under immense mechanical stress. Governing all of this physical violence is a single international standard, ISO 9001. Yet, if you look up the rule responsible for managing this entire industrial ecosystem, Clause 7.1.3, you will find exactly 2 sentences. Those 2 sentences contain 3 specific directives. To manage infrastructure, an organization must determine, provide, and maintain it. On the surface, that sounds like a basic shopping list. In reality, it forms the x-axis of a massive operational matrix. The standard's definition of infrastructure spans the entire factory ecosystem. We must apply those 3 verbs to everything from the building itself and the transport vehicles to the software systems and specific hand tools used on the floor. Then we apply the second multiplier. These actions do not happen once. They must be executed across the entire life cycle of each asset, from initial setup and testing, through daily operation, and eventually to decommissioning. By multiplying those 3 axes together, a 2-sentence rule instantly expands into a matrix of roughly 50 distinct operational nodes. Notice that software and IT are not separate categories handled by a different department. In modern manufacturing, a machine's physical hardware and the software required to run it are fully integrated nodes within this exact same matrix. Organizations that treat compliance as a linear, one-time checklist inevitably ignore large sections of this grid. They buy a machine but forget to plan for its software updates, or they build a facility but fail to account for the consumables required to run it. These blind spots become hidden operational liabilities. Clause 7.1.3 is a rigorous, multidimensional engineering blueprint for total asset management. To see how it functions in practice, we have to isolate the individual nodes. The first directive is to determine. This is the act of translating product specifications into exact machine capabilities. It requires precise mathematical calculations, not simply selecting a model from a supplier's catalog. This phase presents a severe capital expenditure trap, especially for new ventures. Eager to capture a market, organizations frequently over-engineer their production capacity before actual demand exists. Look at this chart. The line represents real-world market demand, volatile and slowly rising. The massive block columns represent the immediate capital expenditure of buying high-capacity machines up front to meet projected rather than actual sales. When factory output remains low, that massive gap between capacity and demand turns into stranded assets. The machines sit idle, depreciating in value, while the initial purchase price drains the company's cash reserves. A calculated determine phase solves this by specifying a phased investment strategy. By purchasing equipment in smaller, scaled increments, the factory's physical capacity stays tightly aligned with real-world growth. This calculation becomes even more critical when moving away from standard catalog machinery and into bespoke equipment, like custom injection molds or specialized welding jigs. Standard industrial machines arrive with thick OEM manuals. The original manufacturer has already determined the operating limits, maintenance schedules, and power requirements. Custom tooling arrives with nothing. Because custom molds lack those manuals, the organization must assume 100% of the engineering burden. You have to design the geometry, specify the metal hardness, and validate the thermal tolerances internally. Failing to scientifically determine these physical limits internally guarantees systemic failures on the production line. If you do not know the exact thermal limit of a custom mold, you will inevitably melt it. The determine node forces an organization to manage risk and execute bespoke engineering. It ensures that what you plan to build is physically and financially viable before a single dollar is spent. The provide directive is an exercise in strategic operational trade-offs. It requires a calculation of the total cost of ownership, balancing the initial purchase price against the long-term technical debt and resource consumption of the hardware. The origin and brand of the equipment you source instantly change the operational realities of your factory floor. This radar chart maps 2 distinct equipment profiles. On the left, equipment A represents heavy, highly durable industrial machinery. It runs forever, but it is incredibly noisy and consumes massive amounts of power. On the right, equipment B is highly cost-effective up front, but carries a much higher risk of defects and component failure. The initial choice during procurement permanently dictates the factory's future. Selecting the cheaper equipment on the right immediately scales up the future burden for spare parts, continuous oversight, and downtime. You pay less upfront, but you pay constantly in labor. Physical hardware is only half the sourcing equation. Modern infrastructure requires operating software to function, and the two are inextricably linked. This creates a severe operational vulnerability known as software lock-in. A supplier may sell you the physical machine, but refuse to provide the source code, diagnostic access, or the rights to install updates. If an organization fails to secure these digital rights during the provide phase, they are effectively only renting the capability. The supplier holds the factory hostage for every software patch, while the factory bears all the physical liabilities of the hardware. Providing a machine requires the procurement team to negotiate absolute ownership and control over both the physical iron and its underlying digital logic. Everything built will eventually degrade. The final directive, maintain, is the active, scientific management of that inevitable physical breakdown. We can measure an organization's effectiveness here using a maintenance maturity gradient, categorized into 3 distinct operational levels. Level 1 is reactive maintenance. In the industry, this is known as run to failure. You run the machine until a part slaps, then you fix it. This is mathematically acceptable for cheap, non-critical assets, but disastrous for main production lines. Look at this wear curve. In Level 1, the health of the component drops sharply and hits the critical failure threshold without warning, taking the entire production line offline with it. Level 2 is OEM compliance. Here, the factory relies entirely on strict adherence to the supplier's manuals and predefined calendar schedules. Parts are replaced every 6 months, regardless of their actual condition. These schedules are designed by the manufacturer to minimize their warranty risk, making them extremely conservative. By rigidly following the calendar, factories throw away parts that still have months of usable life, wasting capital. Level 3 is contextual or predictive maintenance. This is the highest tier of maturity. Instead of using a calendar, predictive schedules shift based on real factory stress data. By monitoring variables like vibration and heat, the organization maximizes the component's lifespan and only triggers a replacement right before the failure point. Achieving Level 3 requires data, but it also requires a highly specific human element, the machine operators themselves. Operators must be given responsibility for managing minor daily variances, like clearing jams and adjusting tension and applying lubrication. By handling these daily tasks, they build deep, physical intuition about how that specific machine sounds and behaves under stress. If an organization removes operators from these tasks and relies exclusively on a specialized maintenance team, they create a dangerous knowledge gap. The people who spend 8 hours a day with the machine lose the ability to detect the subtle warning signs of an impending failure. Optimal maintenance is a dynamic feedback loop. It requires raw data, an understanding of mechanical stress, and the daily intuition of the human operators. If we zoom back out, we can reintegrate these specific examples of engineering, purchasing, and maintenance back into the macro view of our original 50-node matrix. Because this infrastructure operates as an interconnected ecosystem, treating these nodes as isolated silos guarantees a systemic collapse. Watch what happens if we trace a single flaw. Suppose the engineering team fails to accurately determine the thermal limits of a custom mold during the setup phase. That initial engineering flaw directly poisons the procurement phase. The purchasing team, working with bad data, provides the wrong grade of industrial coolant to the factory floor. Because the coolant is wrong, the mold overheats, the data spikes, the predictive maintenance schedules become useless, and the machine suffers a critical failure. A failure in one action inevitably neutralizes the effectiveness of the other two. You cannot maintain what was improperly provided, and you cannot provide what was poorly determined. True infrastructure quality management requires the active, continuous orchestration of capital, software, and human intuition across every single stage of a factory's life cycle.